Yeah. So let's get the show on the road.
Yeah. Yeah, let's get started. So our group is called Ptolemy Solutions. I'm Joshua Cotton.
My name is David Watt.
I'm Elisa.
No, I'm Alex.
Yep. And this is our project. Let's gonna click it.
All right. Um,
Isn't there?
yeah. Okay. So yeah, before we get into our design, we want to understand what lunar regolith is and how it affects us. It's defined as that thin particulate that covers the lunar surface. It's caused by billions of years of bombardment of the lunar surface, obviously by um, meteorites. So the chemical composition ends up becoming a mix of the bedrock and the asteroid material itself, other minerals. Um, by this constant bombardment, we get an average grain size in the micrometer range, 60 to 80 micrometers, but this can range to under 20 micrometers, and then large rocks and other stuff itself. As we know, there's no constant weathering process on the moon with no atmosphere, no liquid or anything like that. So we end up getting these fine particulate with coarse and sharp edges, which can cause its own variety of problems. And then, like I said before, there's no uniformity over the lunar surface with the chemical makeup and whatnot. We also have a lot of different geographical regions. So the highlands and the Marias are the main two regions of the moon, which lead to different depths of the regolith itself. In the highlands, we have like 10 to 15 meters of regolith. In the Marias, it's more like 5 meters range. Then we also have a lot of macro features on the moon, such as mountains, ridges, and valleys, and then micro features such as the craters that are everywhere, and then those boulders, like I said before. So all this ununiformity makes it a little difficult to choose a landing site, and then the regolith itself. So like I said, there's a few negative effects that this regolith can cause for our missions themselves. During that initial descent, during landing, a lot of regolith is kicked up in plumes, and this can cause some visual obscuration of the landing sites itself. And then a lot of the instrumentation on board of the landers will use visual confirmation of the landing site to use their instruments, such as velocity and whatnot. So the plumes themselves can cause a lot of different problems when it comes to the landing stage. Then also with this plumes being kicked up, there's a lot of abrasion and sanding going on the landing struts and any kind of other moving parts that regolith get stuck in between. And like I said, very coarse, very sharp, fine particulate that causes this sanding. Once the lander itself is landed, though, there's a lot more complications that would be caused by the EVAs. And once those astronauts start going out onto the lunar surface and staging all their equipment, um, with how fine it is and how easy it is to be kicked up, it ends up like coating almost all the equipment that goes out there, causing more abrasion, causing more problems like that. And then because these astronauts will tend to go in and out of the lander and take off their suits, they'll end up getting covered in it themselves and their clothing underneath. So this can even lead to more serious health concerns as they start breathing it in. And we don't know the chemical makeup. Some of them, there's radiation on the moon. Some of these particulates are from, deep space particles and whatnot. So a lot of health concerns that can be brought up. And the picture here is of Apollo 17 lunar rover that has a broken fender. And as you can see, all over this rover is just covered in dust. So these astronauts end up doing more housekeeping and chores, trying to keep their equipment clean versus the actual science and the mission that they're on themselves. All right.
Okay, so our job is to find a solution to this problem. The first thing we wanted to do was find what our target problem is. We made some research, and astronauts said that from 100 feet of altitude, they could see particles of dust come up. This is from the exhaust of the turbines interacting with the lunar surface. And these are the particles that stick to the sensitive parts of the equipment and cause all sorts of complications. So our job is to reduce the amount of regolith that would be kicked up, thus reducing the density of regolith in the air. That's our main job. And what we came up with was some sort of surface modification so that it would act as a barrier between the surface and the thrust exhaust. Okay, so one of the competition requirements was to decide a lander. We had two options, the Blue Origin Blue Moon lander and the SpaceX one. We went for the Blue Origin one for a couple of reasons. The first one was its mission was way simpler. It had way less point of failure. Also, the thrusters was a main one. These ones in the Blue Origin one are in the bottom, whereas the ones in the SpaceX lander are in the midsection, and that would interfere with the design we came up with. Also, the Earth atmosphere is a non-factor. Okay. Now we defined our constraints. We had budget for the total contract cost of this lander was 3.2 billion. So we decided to make a maximum increase of 5%, which is 160 million as our limit. Then the payload capacity is 20 tons. We wanted to make that, we wanted to use as much as 15% of that, which gives us a limit of 3 tons. It also had to be non-toxic, whatever we come up with, couldn't affect astronauts' health and shouldn't be corrosive, like minimal corrosion. Had to be ready in 3 to 5 years. The technology shouldn't be too advanced. Had to be versatile. Would be ideal if we could apply it to many different landers. And sustainable, should survive many ascents and descents to the moon, and easy application if the astronauts could make as minimal as interference as possible and would be automated, that would also be ideal. So this is what we came up with. We called it the LSPS, the Lunar Surface Preparation System, and it consists of 2 parts. We have the capsule here, and then the railing, which is the cage. Okay, so the capsule has 2 compartments. The top chamber inside of it contains a tarp. This is what will act as the barrier I talked about earlier. And then the bottom chamber is designated to opening the capsule. It will be pressurized to create a force that will expand the quadrants and make the tarp expand. And then it will open with a wheel lock mechanism. This will be timed. And the railing contains the capsule during takeoff from the Earth and then the trip to the moon. And then during landing, the landing stage, it will have a release mechanism. We'll release the capsule, then the capsule will open. And this is what my colleague here will explain now.
Yeah, so functionally, what is going on here is as the lander begins its descent, our system, there will be 2 identical copies of it on either end of the lunar lander. There will be a staggered release of the two capsules at about 100 meters from the surface of the moon. These are going to pretty much be deployed and then open up towards the ground. Once they open, what you're essentially going to be doing is we'll be releasing our zirconia tarp, which will then act as a barrier that, while not intended to survive the flames of the lander's engine, it is intended to spread the kick up of regolith itself and essentially decrease the amount of contact of that kicked up regolith with the lander during the descent of it towards the moon's surface. Now, looking at the railing itself, this thing is made of aluminum 6061. It is entirely entirely fastened by blind rivets. It has a mechanical release, which this is a render without the top of the containment. As you can see, the release, which we'll get into in a sec, it's a mechanical release of the capsule itself, which is driven by the power of the lunar lander itself. So this thing will be connected to the power of the lander through the lander's payload. As the payload bay, which is the top section of the Blue Origin lander, that is where this railing system will actually be connected. Now onto that attachment. Once again, we'll attach it right to some of the shielding of the payload on the lander. The attachment of each railing system involves 2 separate pillars of the railing itself. Each pillar has 8 fasteners. These are once again blind rivets. Moving on from there, close look at how we actually release the capsule. So the capsule is going to have an extended diameter. This is a side view right here. As you can see in this top view, the blue is going to be those clamps, which are designated by A and are being pushed out here. Each motor is a step motor. They're going to drive a shaft turn a shaft linearly, which then pushes these the things marked B, those linkages, those are going to be pushed forward, which then pulls, or then sorry, that then pushes the clamps outward. So essentially these are reversible. We chose step motors that we could then determine the exact distance that we want to move the clamps, because you see when it comes to this design, while the capsule tarp that it contains is not reusable, the capsule itself may be reusable. The railing most certainly is supposed to be reusable. It's supposed to last 3 to 5 missions, or 5 missions, sorry. And on top of that, how that works is you'd essentially be able to reload it either on Earth or in zero gravity, because from the top down, you'd be able to put a capsule into the railing. Then you would have what's called I'd say called the loading range. So pretty much that distance here is the inward position of the clamp. So then it could catch the capsule while being loaded into the railing. And then you could then clamp it fully by moving it all the way in. And then when we want to release the capsule, we pull it all the way back. And then the force of gravity on the moon, which is not very strong, would still then pull the capsule towards the lunar surface as the lander is descending.
So here we have the capsule by itself. We decided on aluminum 7075 due to its high weight to strength ratio and low cost compared to other materials. The capsule is divided into 2 chambers, so an upper chamber and a lower chamber. The upper chamber houses the zirconia tarp, and the lower chamber is pressurized and houses the wheel lock mechanism that causes it to open and expand. Additionally to being separated into an upper and a lower quadrant, it's separated into, an upper and a lower chamber, it's separated into 4 quadrants. So each quadrant is attached to one of the corners of the tarp, so that when it expands like the 4 corners out away.
Right. Also look into the wheel lock mechanism. So as Giovanna said, one of the key parts of this design is that all 4 quadrants are completely independent as they're attached to the 4 corners of the tarp, need to be spread out. So when we first came up with this design, we need to come up with a way to give those quadrants the energy to be spread out to the 4 different corners. So we tried to brainstorm a few different ideas, such as combustion. We ended up landing on pressurization itself, as the internal surface area, it'll distribute an equal force to all 4 quadrants and be able to spread them fully apart. The next part of this was designing how are we going to timed release that pressure, which is where we came up with the wheel lock mechanism itself. The way I like to think about this is more like a child's lock on a pill bottle. So we have 4 different parts to this wheel lock mechanism. There's the base plate itself that has flanges that are integrated into the capsule itself, not attached, but integrated so that the base plate cannot spin. And on top of that is mounted the wheel itself, which is able to have full rotation. And then on top of that is the base plate, which houses the motor, the battery itself, and then the relay system to activate it. So the key is that wheel itself, and on each of the 4 quadrants are these pins, and the pins will slide into the wheel, and then with a twist, it'll lock them into place. So that's like the child lock in the pill bottle, like I was saying. So the motor itself, once it's remotely activated, will just twist 10 degrees, allowing those pins to have full to exit the wheel itself, and then the pressure will take over and spread those quadrants out to their full distance. So we chose a pressurization of 2,000 pascals because the lunar surface itself has no atmosphere and has no pressure. So the pressure gradient was the most important part, with near 0 pascals. And we didn't need much energy itself because of the weight of the capsule, which we'll get into and all that. So we chose on 2,000 pascals, which will release just before the lunar surface itself, give those quadrants enough velocity to spread out to its full width, and then land. And those quadrants will act as anchors to the lunar surface itself.
So here again, we have an image of the individual quadrants. As you can see, the hooks that the tarp attaches to at the top. We originally chose the exact same material that we used for the outside of the capsule, but we changed that to aluminum 1060O because we want to have a factor of safety of 1.5. We have a width for each of the capsules, because there's 2. We chose a width of 0.44 meters in diameter. This comes from the fact that we know that the Blue Moon lander is transported using the Glen rocket. Yeah, and which is 7 meters in diameter, but the Blue Moon lander is 5 meters in diameter. So we didn't want them combined to take up more than 1 meter in diameter, so both of them are 0.44 meters in diameter. We had
the most leeway with our height, and we ended up using a height of 0.92 meters. This was we calculated this based off of like how big the tarp was and how much room we would need to fit it inside of the capsule. And it's just showing the entire structure by itself.
Absolutely. So going to a little bit of structural analysis, specifically with the railing, the biggest worry that we had were the actual forces of the ascent of the New Glenn rocket from Earth to the atmosphere. This is where we'd have about 3.21 G's of force. This would be, we figured, the most amount of force that this structure would ever be under, just because the lunar lander itself would not have that many, the G's would be lower on the moon, and not to mention, it's just the structure, there wouldn't be really any other situation for something worse. Now, to that end, we wanted to make sure that these railings would survive. We chose 18/8 stainless steel, and we were able to reduce the number of rivets per panel, so per red mounting surface, if you will. As you can see, there's more rendered here, but after analysis, we reduced the number of holes and therefore the number of fasteners needed to about 8 per. This got us under to a factor of safety of 2 for whether or not these each of these railing pins would then fail, whether or not they would fail like due to the forces of gravity. So pretty much the force of gravity of 3.21 G's while during rocket ascent, that divided among each of the rivets came out to about a factor of safety of 2 for each individual rivet, if that makes sense.
Yeah, and just like David was talking about, this is an analysis of the hooks that hold the tarp in the upper chamber of the capsule. There are 4 hooks total, and the weight of the tarp is assumed to, on average, equally hold a fourth of the tarp's weight, and the hooks are going to experience most of the highest stress during the takeoff from Earth, just like David said, and this will and this was assumed to be fixed to the top of the capsule. And with it being fixed, the total stress added from the tarp to one individual hook was 20.64 megapascals. And the material chosen, like Giovanna mentioned earlier, was aluminum 1060-0, and that had a yield strength of 30 megapascals. And applying maximum shear stress theory, the factor of safety is derived to be 1.45. Now, originally, I had the hooks made of aluminum 7075 T6, the same material as the capsule. However, that gave a factor of safety of like above 20. So for the purposes of material optimization, we decreased it to aluminum 1060-0 for a more optimized design. Okay, so the thermal analysis, the main issue here is radiation from the sun. The amount of heat that the motor internally that turns the wheel lock produces a very insignificant amount of heat. So our main issue is okay, how much based on radiation is the outer part of the capsule going to heat up, and then based on that temperature, how much conduction is going to occur, and how much heat transfer is going to go into the capsule. So essentially what we have here, our target temperature inside the capsule is 5.4 Kelvin, and we need that so that we can maintain that 2000 pascals pressure within the bottom chamber, which we need that pressure to be around that area, because if it heats up too much and there's too much pressure, it could expand very rapidly and then buckle and pull back on itself, and we won't have the full coverage. So from the radiation, we calculated that the surface temperature at a maximum and it is 39.7 Kelvin, and we get this number based on for example, if the Earth is I think at its perigee point, and then the moon is at the apogee point based on Earth to sun and moon to sun, this is when the radiation from the sun's the highest, and it's going to heat it up to that temperature. And that temperature based on conduction is going to generate 7,700 kilowatts of heat transfer into the capsule, and that is because aluminum 7075 is a terrible insulator. However, we chose to layer it with 3 layers of Cryogel Z insulation, which is about 15 millimeters thick, and that reduces it significantly all the way down to 474 watts. And with that amount of wattage going into the chamber, the internal temperature heats up to only 5.9 Kelvin, which keeps the pressure near the target range of 2 kilopascals.
Right, so we've shown you all quite a dense design here, and the real question is, can it even work, right? So take a moment, kind of imagine if you look on a picture on the right, we have essentially two plots of 3 by 3 meters of lunar dust. Now, the reason I bring this up is because during the Apollo missions, it was reported that from about 100 meters up, the astronauts could actually see lunar regolith at their window. So this regolith was already being blown up and contacting their lander from that high up from the surface of the moon. With that in mind, we decided to assume, given the depth of footprint for someone on the moon was about 5 to 7 centimeters. So we taking about 7 centimeters deep, plots of 3 by 3. That total mass of lunar regolith, which would then be seen up to the windows of the lander, would be that's about a mass of 1890 kilograms. Now, essentially, what we do is by adding the tarp, what we're doing is we're essentially spreading out or spreading those initial kick-ups of dust further away from the lunar lander. And so in theory, what's going to be happening here is that then that same amount of regolith will then be spread amongst a larger volume, which will therefore then decrease the amount of contact density with the lunar lander itself. And through our math, while very crude, it came out to about, we're reducing regolith under these assumptions by about 49%. Contact the regolith with the lander by 49%.
Yeah. So for our final slide, we are going to go over the final specs of our design and how they compare with our goals. So for one capsule and railing system, that is 218.72 kilograms. And obviously we have two of these. So that is a total mass of roughly 437 kilograms, which is about 2.4% of the payload capacity. Our goal was 15% of payload capacity of 3,000 kilograms. So we were well below our goal for mass. And then the total cost in materials is $21,865. Now, obviously, that's not factoring in manufacturing or labor. Now, however, a lot of the labor is already in the original contract, but nevertheless, with that material cost and the goal being 160 million, there is a significant amount of leeway as far as miscalculations as far as time to manufacture and any extra labor. So we have a lot of leeway with extra costs, and the size of the whole capsule. We actually touched on that earlier. With the railing is 1.66 meters high and about 0.61 by 0.61. And the one individual tarp is roughly 10.5 by 10.5 meters with 9 millimeters of thickness. We did that calculation of 9 millimeters based on, like how much heat is being applied to the tarp. And however, the tarps overlay the ground. They overlap each other. So you're not going to get 2 tarps where it's like, oh, you have a coverage of 20. With the overlap included, it's going to, on the surface of the moon, it's going to be 16.2 by 10.6 meters. And we assumed that the lander is roughly 5 meters in diameter. So that is ample amount of coverage for the lander. And like David mentioned in the previous slide, it should, with a rough estimate, reduce the contact with regolith by about 49-50%. But that is our design, and thank you guys so much for being here and listening. So we're ready for questions.
Thank you.
Okay, so So good job. This is an interesting solution. So the first thing I will note is I've seen teams before and not just this semester, but past semesters talk about their system and the weight it's adding in terms of the overall vehicle weight. And you guys said no, that's not the right thing to do. We're going to talk about it in terms of payload weight. So congratulations, that's the right measure to use. You guys jumped right into the design of your deployment system in terms of physical hardware. What I think is the more interesting engineering challenge is the dynamics of deploying a car on the moon.
I see.
Yeah, I think that deserves way more attention than what you gave. I can imagine that, you know, as you're firing a capsule down and then splitting your canister apart, you're potentially going to bounce, right, and crumple back up.
Right. That's why that pressure had to be a certain range, which we probably should have showed the calculations for that. Just see, like, you know, like we essentially calculate it's like based on the height at which it explodes. We timed it with like the velocity that's going outward. That second that it becomes maximum, it's hitting the ground.
Yeah.
So that's kind of like the dynamics of that.
I would love to see some sort of simulation of that.
Okay.
I think that's something that, like, take my word for it, we look at it, right? I think that's something.
Right.
Show me what you.
Right.
I also want to see. I mean, you said the tarp is made out of zirconium, right?
Yeah, zirconium fiber.
Okay, so I don't know what that looks like. I don't know if that's manufactured. I don't know how effective that's going to be in surviving the plume impingement. Okay. There's a lot there that is engineering interesting to me.
Okay.
So I'd like to see more detail on that. As far as what you did show, you're talking about your pressure. I like that you're thinking about thermal analysis and the effect on the pressure, but you're talking about something that's pressurized to what, 2 kilopascals, right?
Yeah, very small.
Very low, right?
Yeah.
Okay, so are you anticipating that you're going to pressurize seal that in an earth environment?
Yes, I believe we did assume that, which essentially to put that in an earth environment, we would have to make somewhat of it, well, not somewhat, but it'd have to be like vacuumed, because obviously it's like it, you know, because atmospheric pressure is like, well, like 101 kPa. So yeah, it'd have to be a lot smaller on Earth, but then once it gets to the moon, in that context, that's the pressure gradient that we need.
So it's relatively easy to build a tank that's going to be pressurized, right? Because now everything's just acting in tension. That's fine.
Right.
It's more of a challenge to build something that is going to be under vacuum. And so now you got to worry about like filtering and pressure loads and all that stuff. So so consider, although you did mention, right, you're planning on this being down at a temperature of like 5 Kelvin, right? So whatever gas you're pressurizing with on Earth, you know, PV, NRT, you're not going to have a 98 kilopascal difference at 1 atmosphere in an Earth environment, right? It's going to be at, you know, it could be potentially at Earth pressure and then cool and reduce the pressure to 2000 pascals that you're looking at targeting. So, but at the same time, I think requiring to be in such a tight temperature range and trying to do that passively is going to be a challenge. I think because you do have, you know, such massive swings in temperature between, you know, being exposed to sunlight and being in shadow, and you're mounting on the external surface of your spacecraft, right? So you've got a lot of difference in heat impingement. So you might be better off trying to keep it at a warmer temperature, and that kind of minimizes the pressure changes you have to deal with. So consider that. Not to say it can't be done, right? But it's going to be a challenge to ensure that something that's, you know, mounted to the side of the spacecraft is kept in a tight temperature range. Back to the tarp deployment. Your capsule is splitting into 4 pieces and dragging the tarp out with it The edge of one tarp and the edge of the other tarp are going to overlap somewhere reasonably underneath your vehicle. And now you've got big chunks of aluminum sitting there that are potential debris sources.
Sure.
So what do we do about that?
Well, the objective is not to land on top of them. There's a map in one of these.
It's beginning of the collapse slide.
Yeah.
So ideally, we would land further from the ends of the book.
But they're still relatively close to the vehicle. So this if this is a system that you can make it work with the deployment of the tarp, this may be something where you say, you know, on a EVA, go pick those up, and either, you know, stash them, you know, far enough away from the land that you're not worried about them being kicked up by the plume, or bring them back into the vehicle because they're reusable. Although that's extra mass you have to look back to Earth, and you probably don't care about that. But yeah, just, you know, the expectation I think would be that your astronauts would do something to mitigate that risk. Let's see. On slide 14, we were talking about structures, and now we're talking about like my field. Okay, so your load case of 3.21 Gs, I suspect is not going to be what's driving the design here, right? Okay. I think things like this, subsystems tend to vibrate, and I know you're talking about this is heavy, and it was heavier than I was thinking when we were talking about this slide. But I would expect vibrations to be significant here, and so I would look into what the launch vibration environment is. It's going to depend somewhat on where you're located in a ascent vehicle, and it's going to depend somewhat on your mass and how you're mounted to other things. But I would definitely take a look at acceleration. Yes, sir. Or at vibration. Your factor of safety here is 2.06. What's your requirement?
For us, we had an initial requirement, I believe, 1.5.
1.5 on what?
Just that was our general factor. Fair point. We chose 1.5 as the general factor of safety for all designs statically, so in terms of structural. So for that, if we were around that ballpark, then we were happy with it. We kept it at 2.06 just because we wanted the number of fasteners to be not like 4.
So one thing when you're talking about like riveted joints, bolted joints, one thing that comes up a lot is inter-rivet buckling. Okay. And so you generally don't want to space your fasteners out too far, even if you say I can carry the load with fewer fasteners, but if they're spaced out along a long distance, now things start to buckle and not be
like buckling between the fasteners.
Exactly. Okay. And you can, I mean, if you have, do you guys know Vroom? Vroom, VRUHN?
No, sir.
Okay, so if you're doing anything in spacecraft structures, aircraft structures, go look up Vroom. I'm sure you can. I know you can find a copy in a library in Marston, because I actually looked.
I have that one.
Yeah. Okay. Ting's got. Go see Ting. Flip over her copy. I'm sure you can find, you know, on the interwebs a PDF copy that you can look at. Perfect. I know because I have one. But then I got like there's a whole story about Vroom, Northrop Grumman, but we can talk about that later. But get a copy of Vroom. He'll, you know, he lays out how to do inter-rivet buckling calculations. When you're talking about aerospace, and I've not strictly mentioned this in every class that we've been doing the last couple of days, but I'm at least writing in the notes, and I'll mention it here. When you're talking about aerospace structural analysis, you should always be presenting your strength analysis in terms of a margin of safety rather than a factor of safety. You familiar with the difference?
No, sir, not.
Okay, so
would that be like a range of factor of safety, or
so for aerospace, and really for anything, factor of safety should be set out ahead of time, right? It's a requirement you have to meet, and I'll talk about what your specific requirement is and should be in a minute. But your factor of safety is defined for you, and if it's not defined for you, go figure out what it should be and what you're going to work to, right? And then it's 1.5 for you guys maybe. And then you say, okay, the allowable load that my structure can carry is say 1,000 pounds, right? The load that my structure is actually going to see in service, the 99.9 percentile environment, if you got any sort of random variables in there, is say 500 pounds, right? So I've got 1,000-pound allowable, I've got a 500-pound design load, and then I've got a 1.5 factor of safety, right? So I'm going to take 1,000 divided by 1.5 times 500, right? So 1,000 divided by 750 is going to give me what, like 1 1/3, right? And I'm going to subtract 1 from that. So my margin of safety is positive 0.33, positive 33%, right? My structure is 33% stronger than it needs to be to carry the loads with the factor of safety that it's going to see in service.
So it's essentially, this is what's allowable. This is what is actually what it's predicted to be loaded with. Here's the target factor of safety. How much quote unquote extra
exactly that's
do we have?
Right. And
okay.
now I know if your margin is positive, you've met your requirement. If your margin is negative,
I see.
I shouldn't see it. You should go back.
Yeah.
Okay. So now let's talk about what your required factor of safety is and should be, right? So you're saying 1.5, and it's real common to hear, factor of safety in aerospace is 1.5. That is somewhat of a simplification because there are different ways that structures can fail and different levels that we care about that.
Right.
So for a metallic structure, I would see typically a 1.5 factor of safety on ultimate failure, right? So you're talking about, something like tearing, something collapsing, buckling type of failure. And on something like yield, I would typically see, in my world, it's usually 1.15. I know in some spacecraft, it might be as low as 1.1. Right. Okay. So an ultimate failure mode and a yield failure mode are two different things that you care about to two different levels. And so the two different standard factors of safety. So on the next, and I kind of, I shot my water a little early, right? So on the next slide, I think we were talking about the hook analysis.
Yeah.
I was going to ask you.
Which, by the way, I think all of our factor of safeties and all that is based on yield. So we did like 1.5 for yield.
So that's just going to ask you, right? So
which is pretty high now that you're telling me it should be like closer to 0.15.
Is 1.45 acceptable? Right. And here you're doing again a comparison to a yield allowable. So 1.85 acceptable.
Right.
Yeah, it probably is, right? Because the requirement probably is 1.1, 1.15. Should be defined for you. And if it's not, go ask your customer, right?
Gotcha.
Right. So, okay. So that's structural analysis. I like that you're doing, hand calcs, curved beams are maybe a little more complex than what we're considering here, but you're doing, the right type of thing. I'm glad you didn't do a FEM. Let's see. The other thing is, because you do have two different requirements for yield and for ultimate, you should be checking both.
Okay.
You can make an argument to say most aerospace materials are going to be ultimate critical, because if you look at the ratio of the 1.15 to 1.5 factor of safety versus the ratio of like an ultimate allowable to a yield allowable, usually most aerospace materials are going to be ultimate critical. So typically, in my world, we'll do an ultimate analysis and, maybe not even write down a yield analysis, just say, the ratios mean that we're good in yield. Let's see. So on thermal analysis, right? You said you were going to have like 7,700 kilowatts of power coming into this thing. How big is it? Like, what's the surface area? Or the projected surface area that would be exposed to the sun.
So I believe the surface area was about I think it was 1.51 square meters.
Okay.
Yes, I think that would be correct.
Yeah. So where does 7,700 kilowatt?
Yeah. So that comes from what's that equation? It's like the Boltzmann law, the
radiation equation for
so that's solar radiation.
Yes,
right?
sir.
Okay. Yes. Yes, that's solar radiation that okay. I'm sorry. That's not solar radiation. So solar radiation heats up the surface to that. And then I was imagining if the surface gets up to that at a maximum, there's going to be like through the thickness of the aluminum, there's going to be conduction from the surface to
so
the
you're not
inside.
touching the surface is like a fixed constant temperature. Okay. So I remember from the Mech 2, Mech 3 series a couple semesters ago, they were doing like heliostats, right? Which is like sun tracking mirror that's supposed to reflect power back to like a central collecting station and heat up molten salt or whatever. And I got a little bit familiar with like insulation, right? So like at the surface of the earth, the best you're gonna get at like high noon, you know, in the tropics is like a kilowatt per meter squared.
Yeah.
Right. And that's somewhat reduced by the fact that, you know, the sun's coming through the atmosphere, but at the top of the atmosphere, you're something like 1.5 kilowatts per meter squared.
Okay.
So your 7,700 kilowatts seems like that's way, way high. Right. Like, I mean, I don't know where that heat's coming from. It's not coming from the sun. It's not coming from, you know, any systems on the spacecraft, right? I mean, they shouldn't be generating that much. So I think that is.
Well, I think I know that the temperature that it heats up to, and I might have to double check the conduction, but are you familiar with like solar irradiance?
Yeah.
Okay, yeah. So I think on the moon, like from one peer-reviewed paper that I saw, the solar irradiance like maximally was like 1,400
watts.
I think it's watts per square.
Yeah, so you're like,
so it's still
1,000 times that,
right? It's still So I think it was watts.
I'm pretty sure it was.
I'm pretty sure it was watts.
Earth and the moon aren't that far apart to where the moon
right.
more than the Earth.
Right.
So yeah, I think that's probably way more heat than you're gonna see. Let's see. And we kind of already talked about the other thermal aspects of this.
I think might come from the fact that the gradient from the outside to the inside is 397 to 5 Kelvin, and like that's what's causing such a massive influx of heat.
Well, the thing, maybe. I think your like temperature is going to stabilize somewhere in the middle, right? You're not gonna like dump in 7,700 kilowatts because maybe you will, right? Maybe it's like an instantaneous, you know, if you actually had the outside surface at 400 Kelvin and the inside you know, pressure chamber at 5.4, maybe. But like
I'll definitely double check it.
Yeah. Talk to like Dr. Trom or somebody, you know, got some familiarity with with heat transfer calcs, because they're smarter about it than I am. But that
just thermal's a little shaky, so it's
so is mine. Yeah. Let's see. Then on slide 17, you were talking about the effectiveness of this.
Sure.
And I think I like what you did. The fact that, you know, it's very difficult to model something like plume impingement,
right?
And where that's actually going to transport debris to. So the fact that I think what you're saying is we're gonna kick up the same amount of dust, but it's going to be in a wider, you know, diameter area.
Yes, sir.
And so let's just figure out, you know, if you have that same amount of dust, which should be a conservative estimate, in that wider area, what is the result? So I think that's a reasonable approach to it at like a first cut. I'd definitely be interested. I know it'd be difficult, but I'd be interested in seeing like an actual debris transport kind of analysis. And I think again, the effectiveness of the tarp, I'm not convinced is gonna survive, you know, a plume hitting it. And right. So I'd definitely like to see more about that. Let's see. Okay, so 430 kilogram mass, right, which is way under your target. I'll say that a 15% reduction in payload is the right way to measure it, but it's a lot, right? Now we're talking about like a 2.5% reduction in payload. Still a lot, but like if you started out with 15%, now we're breathing a sigh of relief. Like, oh man, that's way better than we thought.
Yes, sir.
So that's good. But where does that mass come from? I didn't see anything like a mass budget here.
Right. So right now the Blue Moon lander crewed is going to carry 20 kilotons, uncrewed 30?
No, I'm like your mass of your
my
structure,
bad.
right? What of your structure makes up 437 kilograms?
So that is, so that's accounting for the fact that we have two of these systems. So we just went through the analysis of one because it's the exact same theoretically. That is is your question like
Like how much do your rails weigh? How much do you?
oh,
weigh?
got you.
Yeah.
Yeah, so it is coming from the railing, the capsule, the tarp. The tarp's only 9 kilograms, by the way, which I know you need to see more of that, but its density is only 80 kilograms per cubic meter. It's very low density. I mean, think of that compared to water.
Yeah.
Like
So you're in the neighborhood of 400 kilograms of structure.
I think most of it's coming from the railing. If I do remember correctly, I think that the capsule itself was 59 kilograms.
Okay.
So I think the majority of and if you're thinking of just like one structure, like that's one of them. So the majority of the another 150 is coming from the railing. So
Gosh, that seems like a lot.
Roger that. Roger that.
It feels like, I mean, just eyeball and I, getting scale and thicknesses of everything is difficult to do from a presentation like this. But if you're deploying a 9 kilogram tarp or 2 9 kilogram tarps, that just seems like a lot of additional structure to support that. So I think
I got you.
Roger that. Yep.
I think that should be lower. And not that you didn't like measure the mass of what you got correctly, but I think you'd probably design something that would be lighter to effectively deploy it.
Yeah.
And then like physical packaging of this, right? So you've got these 4 foot like additional diameter on your capsule, right? Because you've got something like 2 feet, 0.61 millimeters or 0.61 meters on one side, 0.61 meters on the other side. Yeah. The diameter of the capsule by ballpark 4 feet or so.
Yeah, that's about right.
What does that do to fitting the capsule into a launch vehicle?
Right.
So can that be accommodated?
In theory, it should. The diameter of the payload bay for a New Glenn rocket is 7 meters. So it's just so grand. I don't know the equation for a conical surface, so I can't tell you. When does that become too small to fit that, nor how high does Blue want to stack their payloads. So admittedly, I'm not sure how to get that information. But what would you recommend in still proving that this can fit within the?
I think it would be fairly simple to get like a ballpark size of the new whatever is it, New Glenn, I don't know.
Oh yes, sir.
Yeah. And even if it's not published, I'm sure there are like renderings of it.
Yeah,
it's it's 50 feet high, so we can like scale up
which
I don't pixel in Microsoft Paint.
Yeah, got it.
I'm sure you have better tools to do it. But get an idea of the size. It should be relatively easy to find, the fairing size of the rocket. That tends to be, stuff that rocket manufacturers publish because they want to be able to sell people on fitting inside of that. So, and just ballpark. I would be surprised if you have 4 feet of space to work with. But maybe you do. If you don't, maybe you've got to, find some other way to package these for launch. Maybe they're stored inside the lander because you don't have astronauts inside the lander at launch. And then it's a like manual operation to come and clip them on to the side of the vehicle, right? So either way, right? Whether they're permanently there or like mounted inside, provisions for mounting is something that we didn't really talk about. So so how those actually would be mounted to a vehicle and why it's okay to do that on a vehicle. And then the last thing I wanted to ask about was you showed these things. You've got your 10 meter by 10 meter tarp, right? And you're gonna put 2 of them on the ground, and they're gonna overlap and form a rectangular covered scheme, right? So why not square?
Okay.
Yeah. Like, doesn't it seem like the plume is gonna kind of go equally in all directions, and why wouldn't you want to try to square that off?
The main problem we had with that one was that these the capsules are mounted to the side of it and they're just falling straight down. So we didn't want like an off-center landing surface. That's why we ended up dropping 2, so it'd be equal in the center. but we also needed the tarp to be square itself because the pressures are acting equally on every quadrant. So there was no way for us to like, if it's rectangular shape, direct two of them more in the X direction versus the Y direction and whatnot. So we just wanted like a uniform square tarp. We also wanted two of them to provide an equal area underneath. And so it just kind of turned out to be
I think
rectangular.
If you're a customer and we could tell you that we could keep the same total mass for them, but with through 4 of them by reducing to get the structural mass to a better number. That same weight, would that justify, would you say, 4 tarps, which would then increase complexity, but would probably get to more of a diamond proper.
So essentially,
ideally you want to be more like a circle,
right?
But it's
right.
hard to.
Then we have 16 anchors, also 16 quadrants.
You would have 16 quadrants. That's true.
Right. Yes. So I don't know if this diagram was gone over much detail, but that is roughly the size of the lander, and then this orange one's a tarp, this yellow one's a tarp, and remember these are being attached to the side here, and they're dropping down from there.
Yeah.
So imagine the yellow not being there. If the lander theoretically just keeps going straight down, it's going to land way off center. So that's why we added a second one. But then I guess if you wanted like a more more coverage in this direction, you could potentially add 2 more here.
Yeah.
But
okay, so then let me.
But then we were just thinking that's just more possibilities of failure.
Yeah. So since you brought that up, that kind of triggered your thought, right? So
okay.
As you're landing, right, are you anticipating New Glen's going to come straight down?
Yeah.
Yes and no.
Okay.
Yeah. New Glenn. So this lander separates from New Glenn, the rocket. Then the lander. We are actually. We went into some old reports, figured out the reason why we chose 100 meters is because based off of previous NASA missions, once they had they would have like their topographic map. Now they got good at kind of they weren't like perfectly vertical, but in terms of like the horizontal velocity was at its lowest by the time you were about 100 meters off the surface.
Yeah, is that and
the majority of the time it is
right?
Yeah,
it's the capsules are going to get kicked out with that same horizontal velocity, right? So things are going to be moving. Mm-hmm. But if your rocket's got to slow down to 0 horizontal velocity,
yes,
at some point,
right? So hopefully, so you may have to figure out some sort of steering, whether that's an initial, mount them at the right angle so they're aimed in the right place.
Yep.
Or some controllability to say, all right, we know we're coming in at targeting this spot over here, so let's fire the capsule so they get to this spot over here as we're going faster and then slowing down as we're coming, right? So some sort of steerability if you're not anticipating just a straight in kind of thing. And then the other thing is if it's traversing the edge of your tarps as it's coming down, if those are now getting kicked up and even that overlap in the center is potentially getting kicked up. So so this again back to the deployment dynamics are of interest. So
and the idea behind us using a railing versus just like a dead drop so that we kind of give it some direction to its velocity before it comes out. Versus a dead drop, it might just kind of rotate or go do whatever it needs to do.
Okay.
That's the idea of the railing. So
all right, that's all I have that I desperately need to say. So things got done.
Thank you
much.
Can you go to your structure analysis? Sorry, I don't have my glasses, I cannot see the page number.
Which one? This one or the next one?
Both. So this from this one, I feel like this is just minor thing here. I don't know why you put dxdy there. What the purpose of the thing?
Right. So what I want to do right here is this is the center of gravity, and then this is with the center of gravity with the capsule is right here at 0. So I wanted to the distance from there to where the pin hit.
Yeah, but we didn't explain anything about that in the presentation. I mean, if it is not in the explain the presentation, it's going to put it there. It's like confusing everybody. Next slide. And first, I don't know what the difference of sigma z and sigma zz. Second, the direction of sigma z they are wrong. If you consider that is x direction, z is downward direction, and then now your a should be positive y direction, and your sigma z direction is wrong. And also you mentioned
Yeah, the direction is wrong.
Yeah.
And also you mentioned that the first you use 77.526 as the structure, and then because your safe factor calculator is higher than 1.5, and you change to 1000 series. First, I don't know. We normally don't use 1000 series for structure.
Yeah.
Like,
Yeah, annealed aluminum is nice and soft, right? So,
Yeah,
if you can get something like 6061, 7075, where it tempered and higher strength, right? You're gonna be able to optimize the structure, right? Because they're gonna be the same density and one strong.
Right.
yeah. So I know that you do well when you calculate safety factors higher than your target. You try to do optimization, but the optimization can be done by reducing size. But not like changing a lower, like you put the year strength is 30, change to lower year strength. I mean, first 1000 series we normally don't use for structure component. Second, most of the time we optimize the structure by reducing the size, and at the same time you can reduce the weight, and of course everything related to spacecraft, reduce the weight is also a good thing. And if there's a specific reason that it cannot reduce the size, just justify it. But I normally don't see any like 1000 series for a structure component.
Okay.
And for the thermal control analysis, because you do have motors, you have the power supply, have you ever considered like those may also generate heat in addition to like some radiation?
So so I'll tell you what, we did consider, what we determined was the time that the motor would spin on the wheel lock was like almost negligible, just because it was only a 10-degree rotation.
You can, oh, okay. If it's like compared to the sun radiation, if it's like really, really small, maybe show some number to you.
Yeah.
When there's some power supply to your system, we would consider all the power that generated in your system will eventually convert to heat, right? So you may need to consider, well, if it's like significantly smaller than the sun radiation, then yeah, tell me the number. So I can, yeah. That's what I have.
Awesome. Thank you.
Great job.
Yeah.
Do you want me to take a picture for you guys?
Yeah, sure. Yeah, let's get what's a good
This one.
Both sides.
This one.
hell yeah.
Awesome. Just wrapping up, cool.
Love this side. Can I get that?
Yeah.
Thank you. Thank you.
All right, now how
I can post direct.
recording to the cloud.